Hi, and welcome back to my YouTube channel. In this video, we will cover essential knowledge for any engineering, fundamentals of electricity. We will learn how electricity works, starting from the very basic things like electric circuit, voltage, current, resistance, inductors, electromagnetic induction, capacitors, transformers, frequency, and much more. So let's start with electric circuit. Electric circuit is a path that electrons pass between the two terminals, the positive and the negative terminals of a power source. We can add things into their path, like light bulbs, and this means that the electrons will have to pass through the light bulb in order to get to the other terminal. In this way, we can create light. The electric circuit can either be open or closed. Closed electric circuit means that the electrons can flow around. Open electric circuit means that the electrons are not able to flow. Voltage is basically work needed to move a charge from point A to point B in the electric circuit. It's like pressure in a water pipe. The more pressure you have, the more water can flow. The more voltage you have, the more electrons can flow. So, what is a volt? Volt is potential difference between 2 points that will impact 1 joule of energy per coulomb of charge that passes through it. Joule is a measurement of energy or work, and coulomb is a very large group of electrons. Maybe we will better understand what a joule is and a coulomb is with an example. So, a 9-volt battery can provide 9 joules of energy in the form of work or heat per group of electrons that flow from one side of the battery to the other. In this case, the current of electrons flow from one side of the battery through the LED light bulb, which produces light, and then the electrons flow to the other side of the battery. Therefore, 9 joules of light and heat is produced by the light bulb. Electric current is the movement of electrons through an electric circuit. When a circuit is closed, it means that electrons will flow through a circuit, and when the circuit is open, it means that no electrons will flow. We can measure the flow of electrons, just like you can measure the flow of water through a pipe. The flow of electrons or electric current is measured in amperes or amps. 1 ampere can be defined as the unit of electric current, and it is equal to the flow of 1 coulomb of charges per second, or 1 coulomb per second. As we already know, 1 coulomb is a group of electrons. The group is incredibly large, and is approximately 6,242 quadrillion, and this large group of electrons must pass in 1 second to be equal to 1 amp. Because of this large number, electrons are grouped together and called 1 amps to make it easier for engineering. Electrical resistance is a force that counteracts the flow of electrons, or electric current. In this way, it serves as an indicator of how difficult it is for current to flow. The electric wire which carries the electrons will naturally have some resistance. So, we will mention some relations like the longer the wire, the greater the resistance, the thicker the wire, the lower the resistance. Furthermore, different material has a different resistance, such as copper wire has less resistance than aluminium wire. Temperature also affects resistance of electric wire. With an increase of the temperature will also increase the resistance of electric wire. Resistance occurs when electrons collide with atoms. The amount of collisions is different from one material to another. Copper has a very low collision rate, but other materials such as iron will have much more collisions. When collisions occur, the atoms generate heat, and at a certain temperature, the material will then start to produce light as well as heat, which is how the incandescent lamps work. Resistor is a component that resists and reduces the flow of current through the electrical circuit. The resistor's purpose is to protect other components from too many electrons flowing through it. Or it can also be used to create light and heat, such as an incandescent light bulb. You will find out more about resistors in one of my previous videos. The link is above. An inductor is a coil, or wire wrapped in a coil. When the current passes through the coil, it will generate a magnetic field. The electric wire will naturally create an electromagnetic field by itself. It's just intensified by the coil. An inductor, or wire wrapped in a coil, stores magnetic energy in the form of a magnetic field, generated by the current in the coil. The magnetic field generated in the coil will go in through one end of the coil and go out through the other end of the coil. This way, the magnetic field through the coil becomes very concentrated. We can increase the strength of the magnetic field simply by wrapping the coils around an iron core. We can also increase the magnetic field by increasing the number of turns within the coils. Also, we can increase the magnetic field by increasing the amount of current passing through the circuit. And this is how electromagnets work. And it's also the base of how induction motors work. You will find out more about inductors in one of my previous videos. Please see the link above. When we wrap wire around a magnet, any change in the magnetic environment of a coil of wire caused by the magnetic field of the magnet will cause a voltage, EMF, to be induced in the coil. This induced EMF will push electrons in a certain direction. If the wire is connected in a circuit, then this electromotive force will cause a current to flow. This is the basis of how AC generators work. Also, electricity at your wall sockets within your home is produced in a very similar way. In my previous videos, you can find a video about the working principle of an AC generator. Link on the screen above. Also a video about physics in an electric generator. Link is on the screen above. For transformers, we can combine all the aspects together that we've just mentioned. We can use one coil of wire around a magnet to generate electricity, and then we can place another two coils of wire, which do not touch, in very close proximity to each other. This composition will create a transformer. Generally, the primary winding of a transformer is connected to the input voltage supply and converts or transforms the electrical power into a magnetic field, while the job of the secondary winding is to convert this alternating magnetic field into electrical power, producing the required output voltage. Now, what's important about the transformer is that we can increase or decrease the voltage between the primary and secondary coils, simply by changing the amount of coils on either side. Again, this is a subject all by itself, and I have already covered this in a more advanced video. The link is above. The next thing I will briefly explain is the capacitor. So, the capacitor consists of two plates separated by thin insulating material, known as a dielectric. When battery terminals are connected to an initially uncharged capacitor, equal amounts of positive and negative charge are separated into its two plates. The basic function of a capacitor is to store electrical energy in an electric field. When the power supply is cut or interrupted, these charges will then be released. This provides a power source, but only for a few seconds. It's slightly similar to a battery. Capacitors are very common, and they're in almost every single circuit board. We have already covered capacitors in one of my previous videos. The link is above. So, the next part I want to cover in this video is that there are two types of electric current, and those are alternating current, or AC, and direct current, or DC. Alternating current is a type of electrical current in which the direction of the flow of electrons switches back and forth at regular intervals or cycles. On the other hand, you've got direct current, or DC, and that simply means that the current flows directly in only one direction. It is not alternating. DC current is provided from batteries, and almost all your handheld devices are from this source as well. So we can convert AC to DC and vice versa using power electronics. And this is how we charge and power, small devices. Maybe it's better to get a closer look at both currents. We start with DC, or direct current. This is the simplest type, and we get this from batteries, solar panels, etc. You can imagine DC current like a river with a current of water flowing in just one direction. The flow of electrons in direct current is from the negative to the positive terminal. Engineers use also conventional current flow, which is from the positive to negative terminal. Conventional was the original theory, and it's still used widely today. It is important that you are familiar with both theories. For electricity to flow, we need to have a closed circuit. Electricity will then always try to get back to its source. When we use the oscilloscope to look at the electrical waveform of DC, we get this flat line, the maximum voltage in the positive region. If we open the circuit, the line drops to zero. If we turn it on and off repeatedly, then we get a square wave pattern between 0 and maximum. If we open and close the switch of electric circuit at different lengths of time, then we will get a pulsating pattern. The other type of electricity is AC, or alternating current. This type is what you'll get from the outlets in your homes and places of work. With this type of electricity, the electrons within the electric wire constantly reverse direction, and electrons flow forwards, backwards, forwards, backwards. You can think of alternating current like the very regular tide, flowing from nil up to maximum in the positive, then flowing back to nil, and then flowing up to maximum in the negative, and then returning to nil again. This pattern is repeated forever. If we follow the electric wires back to the generator, the wires are connected to some coils of wire, which sits within the generator. Inside a basic generator, we find a magnet at the center, which is rotating. The magnet has a north and south pole, or you can think of it as a positive and negative half. The electrons in the wire are negatively charged. Magnets are attracted or repelled, depending on the polarity. When rotating, the magnet passes the coils of wire. Therefore, the positive and negative half of the magnet will push or pull the electrons within the copper coils, and these will also move electrons through the connected electric wires and through the light bulb. The magnetic field of the magnet varies in intensity, so when rotating, the magnet passes the coil of wire, and the coil of wire will also experience a change in intensity of the magnetic field. And this will be from 0 up to its maximum intensity, and then as it passes the coil, it will decrease again back to 0. Then the negative half comes in and pulls the electrons backwards, with the same change in intensity. Each full rotation of the magnet will, therefore, produce this wave pattern, known as a sine wave. The voltage is not constant in this type of electricity. Instead, it repeatedly moves from 0 up to its peak, and then back to 0, then through the negative peak, and finally back to 0 again. What about frequency? Frequency refers to how many times this AC sine wave repeats per second. In North America and a few other parts of the world, we find 60 Hz electricity at the outlet. This means that the sine wave repeats 60 times per second, and each wave has a positive and negative half. This means that the polarity will therefore reverse 120 times per second. In the rest of the world, we mostly find 50 Hz electricity, so the sine wave therefore repeats 50 times per second, and therefore the current reverses 100 times per second. We also have single-phase and three-phase electricity. With single-phase, we have a connection to just a single phase of the generator. So we have, therefore, just one sine wave. With three-phase electricity, we have a connection to all three phases of the generator. The phases are coils of wire, which are inserted into the generator, 122 degrees apart from the previous. This means that the coils experience the peak of the rotating magnetic field at different times. This gives us our three phases, each with a different sine wave slightly out of sync from the previous. You must remember that electricity wants to get back to its source to complete a circuit. As the current is flowing forwards and backwards at different times in each of the phases, essentially, we can connect three phases together and the current will move between the different phases as the polarity of each phase moves forwards and backwards at a different time. Any excess will float in the neutral wire back to the source if needed, and that's only if it's unbalanced. With single phase, we have these large gaps between the peaks, but with three phase, these can be combined to fill in the gap, and therefore deliver more power. I hope that you are now familiar with the basics of electricity, and that you finally know how electricity works. Don't forget to subscribe, like and share this video. Watch the rest of my videos from my YouTube channel. Please consider to support me on Patreon. Thanks very much, and see you on the next video.